Hey guys, all right, so we are on multiplying and dividing radical expressions. So let's look at what we're going to be doing today. We're going to multiply and divide radical expressions. We're going to rationalize the denominator of a radical expression. That means that we never ever leave a radical in the denominator. It's not proper. We got to make sure it's a rational denominator, so we have to rationalize it. And we're going to be multiplying and dividing radicals. Okay, so number 1A, it says complete the table below and simplify the radical expressions in the third and fifth columns. Okay, so let's go ahead and take a look at those. I have A's and B's. The first A and B I have is 4 and a 9. And it says to write this as square root of A times square root of B. Okay, so we'll have square root of 4 times square root of 9. Okay, well, the square root of 4 is what? 2. And the square root of 9 is 3. So that's really 2 times 3, which is 6. Okay, well now they want us to try it a different way. So I'm going to switch colors to do it a different way. They want us to multiply A and B. A and B next to each other means that we're multiplying them. So A is 4, B is 9. 4 times 9 is 36. And now they want us to take the square root of AB. So square root of 36, well, the square root of 36 is 6. Hey, what the heck? They're both the same answer. How about that? So there's two ways that we can approach it and still get to the same spot. All right, let's try the next one. Square root of 100 times square root of 25. Well, the square root of 100 is 10. The square root of 25 is 5. 10 times 5 is 50. There's a train going by because we live on the train, by the train tracks. All right, let's try it the other way where we multiply A and B together. Well, 100 times 25 is 2,500. Squeeze that in there. And the square root of 2,500 happens to be 50. Because 50 to the second power is 2,500. Okay. Third row here, we have A and B, 9 and 16. So let's try square root of 9 times square root of 16. The square root of 9 is 3. The square root of 16 is 4. 3 times 4 is 12. All right, let's try multiplying A and B first. 9 times 16 is 144. And the square root of 144 is a perfect square. The square root of it is 12. So we ended up getting the same answer either way we did this, which means that we are allowed to multiply the inside numbers of radicals. We could keep them separated or we can multiply them, and we're allowed to do that. So this next one, part B, it says use the patterns you observe in the table above to write an equation that relates the square root of A, the square root of B, and the square root of AB all together. So, well, we know if we have the square root of A multiplied times the square root of B, it's going to equal the square root of A times B. All right. Letter C says all the values of A and B in part A are perfect squares. In the table below, we're going to choose some values for A and B that are not perfect squares. So we don't want them to be perfect squares. And we're going to use a calculator to show that the equation that we wrote in part B is true for those numbers as well. So we're going to pick some numbers for A and B that are not perfect squares. So let's see. 2 is not a perfect square. 3 is not a perfect square. 4 is a perfect square. But 5 is not a perfect square. And 7 is not a perfect square. I'm just picking some numbers. We could have picked anything. And I need my calculator. So let me go grab it real quick. So I'm going to pause this for a second. All right, I have to back up a little bit. I accidentally went without recording. So A and B, I picked 2 and 3, and let's see, square root of 2 times square root of 3. Well, the square root of 2 in my calculator is 1.4 if I round it to the tenths. The square root of 3 in my calculator is 1.7. 1.4 times 1.7 in my calculator is 2.38. So I'll write that in. 2.38. I messed up, so I had to cross it out. And then when I took just what A and B are, A times B, 2 times 3 is 6. The square root of 6 is 2.449. So see how close these are? There's a little bit of a margin of error just because we're rounding. So they're not going to be exact because we had to round, but they are pretty darn close. All right, and then for 5 and 7, took the square root of 5 times square root of 7. The square root of 5 is 2.236. I decided to round out to 3 decimal places this time. And the square root of 7 is, to 3 decimal places, 2.646. And we'll have to multiply those together. So 2.236 times 2.646 is 5.916, approximately. So I'll use the wavy equal sign. All right, A times B would be 5 times 7, which is 35. And what's the square root of just 35? So square root 35 is 5.916. Oh my gosh, it's like exact. This one got super exact. So notice how I rounded out to just the tenths in the first one, and it was off by a little bit. But in the second row, I rounded it out to 3 decimal places, and it was spot on. So the more decimal places you round out to, the more accurate your answer is going to be. Okay. So when it doesn't say how to round, you decide how to round. But if it tells you to round to the tenths, then you better round to the tenths. All right, letter D. It says simplify the products in columns A and B below. So I have 2 square root of 4 times the square root of 9. So what I always tell my students is you always multiply outside numbers with outside. And inside numbers with inside. Okay? So if I look at 2 square root of 4 times the square root of 9, okay? First of all, I know what these radicals are, 4 and 9. The square root of 4 is a 2. And there's a 2 out front already, so 2 times 2 is 4. The square root of 9 is 3. And since we're in parentheses here, that means multiplication. 4 times 3 is 12. Okay? Now here's what they did. They did outside numbers with outside numbers, inside numbers with inside numbers. The outside number on the square root of 9 is a 1. When there's no number in front of a radical, you assume it to be a 1. 2 times 1 is 2. Those are the outside numbers. And then for the inside numbers, they're 4 and 9. 4 times 9, so that's why they have it written this way. Well, we know 4 times 9 is 36. So I have 2 square root of 36. And we know what the square root of 36 is. The square root of 36 is a 6. So I have 2 times 6, and it better equal 12, and it does. So let's take a look at the next one. Let's simplify it first. The square root of 4 is a 2, and there's a 3 out front already, so 3 times 2 is 6. The square root of 16 is a 4, but there's a 5 out there already. 5 times 4 is 20, okay? 6 times 20 is 120. Zoom in a little bit. All right, for the next one, they multiplied outside with outside, inside with inside. So the outside numbers are a 3 and a 5. 3 times 5 is 15. Then for the inside numbers, we have a 4 and a 16. 4 times 16 is 64. But we know what the square root of 64 is. So we have a 15 out front already. The square root of 64 is an 8. And then 15 times 8 is 120. Okay. let me zoom back out just a tad. All right, for the next one, 2 squared is 7 times 3 squared of 14. We have, these numbers are not simplifiable. So we can go ahead and multiply. We'll just do the outside with outside, inside with inside. The outside numbers are a 2 and a 3. 2 times 3 is 6. The inside numbers are a 7 and a 14. So let's see what goes underneath that radical. 7 times 14 is 98. Ooh, big number. Okay, so it's going to be the same thing over here. So we'll just draw a little arrow. So let's go ahead and break down the 98. We want to look for the biggest perfect square that we can find. So remember how I told you it's an even number. Always start by dividing by 2 because a lot of times that gives us the perfect square that we're looking for. And there it is. 98 divided by 2 is 49, and 49 is a perfect square. So 2 times 49, those are the droids I'm looking for. Circle the 49 because it's a perfect square. All right, so remember, there is a 6 already out front. The square root of 49 is 7, so we have to multiply the 7, and then you're done with that 49. 2 is not a perfect square, so it's stuck inside the radical. 6 times 7 is 42, and then square root of 2. So that's the simplified version of that third row there. Okay. All right. So this one we could only do in the one way, outside with outside, inside with inside, because square root of 7 is not a perfect square. Square root of 14, not a perfect square. So we couldn't do it that first column way that we were doing it. All right, next page. We're on page 34 now. It says write a verbal rule that explains how to multiply radical expressions. And just like I wrote down on the page right there, we're just going to add numbers to it. We're going to say you multiply outside numbers. The symbol I use for numbers is, it's used to be called the pound symbol. It still is called that. But you guys formally know it as the hashtag. So outside numbers with outside numbers. And inside numbers with inside numbers. Okay? That's how we remember what to do with those when we're multiplying them. Okay? So it says, to multiply radical expressions, the root index, or simply index, must be the same. So if we're multiplying a cubed root times a square root, we can't do that. They have to be the same type of root, okay? And for now, b has to be greater than or equal to 0, and d has to be greater than or equal to 0. So that just means that whatever is under the radical can't be negative. So no negatives allowed. Okay? We don't know how to handle that yet. You will this year, but we don't know how to yet. Okay? So again, under math tip, it kind of goes over the parts of a radical. So this part's kind of important. Coefficient is the number out front. The index is the type of root it is. This one's pointing at a 3, so this is a cubed root. And the radicand is the number that's under the radical. Okay, so all that terminology you gotta know. Okay? All right. Example A is already worked out for us. So let's just go to try these A. Okay? So it says multiply each expression and simplify. I'm going to use the little scratch paper portion on the left to do these problems because this is not going to be enough space. Oh, well, you know what? It might be. We'll try it. We'll see. If we run out of space, we'll take it to the left. So letter A, we have 2 square root of 10 times 5 square root of 3. Remember, outside numbers with outside numbers, inside numbers with inside numbers. So we have a 2 and a 5 on the outside. 2 times 5 is 10. On the inside, we have a 10 and a 3. So inside, we're going to have 10 times 3, which is 30. And then we need to ask ourselves, can we simplify that? Is there a hidden perfect square inside of a 30? Well, 30 is 5 times 6. There's no hidden perfect squares in there. 2 times 15. There's no hidden perfect squares in there. Or 30 times 1. No hidden perfect squares. So this is as low as we can go. How low can you go? And 10 square root of 30 is as low as we can go. All right, letter B. 3 square root of 8 times 2 square root of 6. 3 and 2 are the outside numbers. 3 times 2 is 6. 8 and 6 are the inside numbers. So that'll be square root of 8 times 6 is 48. And now we got to see if there is a hidden perfect square inside of 48. I think that there is. So 48, let's start dividing by 2. We get 24. That doesn't work. Let's try 48 divided by 3. Oops, I didn't put in the 3. 48 divided by 3 is 16. Ooh, 16 is a perfect square. That's as low as we can go, or as high as we can go. So 3 times 16, circle the 16 because that is our perfect square. All right, out front we already have a 6. The square root of 16 is a 4, and then you're done with the 16. 3 is stuck inside. 6 times 4 is 24. So we have 24 square root of 3. And that's as low as we can go. How low can you go? Letter C. 4 square root of 12 times 5 square root of 18. We have outside numbers 4 and 5. 4 times 5 is 20. On the inside, we have a 12 and an 18. Okay, so there's 2 ways that we could do this. We can multiply 12 times 18, or we could simplify it first. Since I've already started multiplying, I'm going to go ahead and multiply it. It's just now that 12 times 18 is going to be a big number. 216. Okay, and we need to see if there's a hidden perfect square inside of 216. So, like I've told you, start dividing by 2. It's an even number, so I know that 2 will go into it. 108 is not a perfect square. Okay, back up. Let's try a 3. 72 isn't a perfect square. Try a 4. 54 is not a perfect square, but 4 is, so that might be it. Okay, so let's try 5 won't work. 6 might work. 6 times 36. 36 is a perfect square. And then 6 is only 2 times 3, so this is as high as we can go. There it is. Whoop, there it is. Do you guys even know that song? It's old school. I was born in the 80s, so I know a lot of 80s and 90s stuff. All right, so there is a 20 out front already. The square root of 36 is 6, so times 6, and then you're done with the 36. And then that other 6 is stuck inside. 20 times 6 is 120. So 120, square root of 6. Letter D. All right, this one has a variable in it. Okay, so outside numbers with outside numbers. We have a 3 on the outside and a 2a. 3 times 2a is 6a. Okay. On the inside, we have a 5a and a 15a squared. Well, 15 times 5 is 75. And a to the first times a to the second, you add the exponents, it is a to the third. Okay, let's see if there's any hidden perfect squares in there. There are. 75. Well, 75, I think, when I think 75, I think 75 cents. 75 cents is 3 quarters. So 3 25s. And 25 is a perfect square. A to the third, we can break that down because 3 is not a perfect square because it's not divisible by 2, but a 2 is divisible by 2, and a to the second times a to the first equals a to the third. And a to the second, because it has a even numbered exponent and it's divisible by 2, is a perfect square. Okay, so there's already a 6a out front. The square root of 25 is 5, so times 5. Done with the 25. The square root of a squared is a. Done with the a squared. So all that's left is a 3 and an a. So under the radical, we have a 3a. Now we just got to clean up what's in front of the radical. Well, 6a times 5 is 30a. 30a times a is 30a squared. Square root of 3a. And that's the answer. Okay. So we've multiplied. Now we're on to division. All right, so we have division property of radicals. So remember how we multiply outside numbers with outside numbers and then inside numbers with inside numbers? The same thing applies for division. You're going to divide the outside numbers together, and then you're going to divide the inside numbers together. Now, b and d have to be greater than or equal to 0 because we don't want to deal with negatives in the radical. Okay. And whenever we have a fraction, remember the one number that is never, ever, ever allowed to be in the denominator is 0. Sorry if that got really loud. I didn't realize how close I was to the microphone, and yeah. All right, example B. It says divide each expression and simplify. So these have been done for us, so you can look at these as examples. Let's go ahead and try these B. So we'll start with letter A, and I think I could do it here. So if I run out of room, I'll just go to the My Notes section. Let me zoom in a little bit. All right, so letter A, 4 square root of 42 divided by 5 square root of 6. So remember, outside numbers with outside numbers. So we have a 4 over 5. 4/5. 5 doesn't go into 4 evenly, so there's nothing we could do about that. Now let's look at the inside numbers. 42 divided by 6. 42 divided by 6 is 7. So under the radical, we have a 7. Hey, we can't do anything else with that. So it's 4/5 square root of 7. Letter B. Outside numbers with outside numbers. So we have a 10 and a 2. 10 divided by 2 is 5. And then let's look at the inside numbers. 54 divided by 2, let's see, 54 divided by 2, that's what, 27? 54 divided by 2? Yeah, 27. But there is a hidden perfect square inside of a 27 because 9 times 3 is 27 and 9 is a perfect square. Okay, so there's a 5 out front already. The square root of 9 is a 3, so times 3, and then you're done with that 9. This 3 is stuck inside. Okay, 5 times 3 is 15. So 15 square root of 3 is the answer. Letter C. 12 square root of 75 divided by 3 square root of 3. So outside numbers first. 12 divided by 3 is 4. And 75 divided by 3 is 25. Those are my inside numbers, so that 25 is on the inside of the radical. And hey, 25 is a perfect square. So there's a 4 out front, and the square root of 25 is 5, so times 5. And 4 times 5 is 20. That was easy. Letter D, 16 cubed root of 8x to the 11th. Over 8 times the cubed root of x squared. So let's look at the outside numbers. We have 16 divided by 8, that is a 2. And we have cubed roots, so I need a 3 in the index there. And let's see, 8x to the 11th divided by x squared. Well, I can cancel out this x squared with 2 of them from the 11. That leaves me with 9. So we'll have 8x to the 9th under that radical. Okay, and let's see if we have any perfect cubes. Well, 8 is the same as 2 times 2 times 2, so there's our group of 3. And 9, x to the 9th, that's a perfect cube because 9 is divisible by 3. Okay, so there's a 2 out front already. The cubed root of 8, in other words, the cubed root of 3 2's means a 2 gets to come out because I have a group of 3. Then you're done with the 3 2's. The cubed root of x to the 9th, well, 9 divided by 3 is 3, so we get to bring out an x to the 3rd. And then we're done with that. And hey, everything came out, so I have nothing left in the radical. So 2 times 2 is 4, so I have a 4x cubed. Nice. A radical expression in simplified form does not have a radical in the denominator. So if it is simplified, you will not have a radical in the denominator. Ever, ever, ever. Okay? That's how you know when you're done simplifying. Most frequently, the denominator is rationalized. To rationalize means to make rational. You can rationalize the denominator without changing the value of the expression by multiplying the fraction by an appropriate form of 1. So I'll show you what it means to rationalize. So example C has an example on it. We'll just go ahead and try them out. So we'll go to try these C. It says rationalize the denominator in each expression. So notice there is a square root of 6 in that denominator. You can't ever, ever, ever leave a radical in the denominator of your answer. So we have to fix that. So the way that we fix it is we need to multiply by the same thing to make it a perfect square. So I need to multiply by the square root of 6 to make it a perfect square. Because anytime you multiply something by itself, you've pretty much made it a perfect square. You've raised it to the second power. But whatever we do to the bottom, we must also do to the top. We got to keep it equally balanced. So technically, the square root of 6 over the square root of 6 is 1. Anytime you have a number divided by itself, that's 1. So we're really multiplying by just a 1. So we're not changing the value of this expression. We're modifying it so that we can simplify it. All right, inside numbers with inside numbers, there are no outside numbers. 11 times 6 is 66, so I have the square root of 66 in the numerator. And 6 times 6 is 36, I have the square root of 36 in the denominator. And the square root of 36 is a 6. So all I have is a 6 in the denominator, but I have a square root of 66 in the numerator. So, moral of the story is anytime you multiply a radical by itself, the number inside gets to come out. So let's look at letter B. 2 square root of 7 divided by the square root of 5. So I need to get the square root out of the denominator, so I have to multiply it by itself, top and bottom, because whatever we do to the bottom, we must do to the top. And let's see, this time we have an outside number, and the outside number in front of the square root of 5, when there's no outside number, you assume it to be a 1. 2 times 1 is 2. 7 times 5 is 35. Radical times itself means the number gets to come out. So it's super quick and easy, as long as we remember all the rules. Letter C. So we need to rationalize 3 square root of 5 over the square root of 8. So I'm going to multiply square root of 8 top and bottom, because whatever we do to the bottom, we have to do to the top. And we're doing this so that we can get the radical out of the denominator. The outside number in front of the radical 8 is a 1, because there's no number there. We assume it to be a 1. 3 times 1 is 3. 5 times 8, they're inside numbers, is 40. All over. The radical 8 times itself means the 8 gets to come out. Okay? Now I can't reduce the outside numbers, the 3 over 8, but I can reduce the square root of 40 because there is a hidden perfect square inside of there. The biggest perfect square inside of a 40 is a 4. 4 times 10 is 40. The 10, if I break it down, is just 2 times 5, and 2 and 5 are not perfect squares, so this is as big as I can go. Okay, so I have a 3 out front already. The square root of 4 is a 2, so a 2 gets to come outside, and then you're done with the 4. This 10 is stuck inside, so I have a square root of 10 all over 8. okay? 3 times 2 is 6. So I have 6 square root of 10 all over 8. And let's see. I know that I can't break down the number inside the radical anymore, but 6 over 8, if I just had 6/8, we could reduce that. So guess what? We can reduce that. 2 goes into 6 3 times. 2 goes into 8 4 times. So my final answer is 3 square root of 10 all over 4. So that one took a little bit of extra work because we had to simplify a few things. So another way I could have done this is I could have noticed from the beginning that 8 has a hidden perfect square. It's 2 times 4, and I could have simplified that first and then rationalized it. But that's just another way to go, okay? So there was not just one correct way to do it. And sometimes doing it that way confuses students. So it might be easier to start off by just rationalizing it and then simplify it. Okay. All right, turn the page. We're on page 36 now. My watch is telling me to stand, which is funny because I am standing. All right, properties of exponents can be used to simplify radical expressions. So these are all the properties of exponents that we have just learned. There's the product of powers property, so product rule. When you multiply like bases, you add the exponents. Quotient of powers property, when you divide like bases, you subtract the exponents, aka cancel things out. Negative power property, anytime you have a negative exponent, you drop it like it's hot. If it's in the denominator, though, you got to throw it up. Zero power property, anything to the 0 power equals 1. Power of a power property, a power raised to a power, you multiply those exponents. Power of a product property, whenever you have a product raised to a power, each term in the product gets distributed that power. And power of a quotient property, same thing. When you're dividing two numbers and they're raised to a power, each number in the numerator gets the power and each number in the denominator gets that power. So still distributing. Okay, so these we all learned in activity 1 and 2. So those have not changed and we're still using those. We use those when we're dealing with radicals because they're related. All right, number 2. It says simplify the expressions using exponent properties. State which exponent property or properties that you're using. So I see we have a cubed root of 8x cubed y to the 6th raised to the negative 2nd power. That's a negative power there. I know it's kind of hard to see. My copy didn't print out super clear. All right, well, it's got a negative exponent, so we're going to have to use the negative power property, which means we got to drop it like it's hot. So when we drop it like it's hot, we assume that this whole thing is in the numerator. And now when we drop it, there will be a 1 in the numerator and a cubed root of 8x cubed y to the 6th raised to the positive 2nd power now. Okay? Which equals 1 over. All right? So because this is being raised to the 2nd power, everything inside the radical is being raised to the 2nd power. A 2nd power doesn't undo a cube root. A 3rd power would undo a cube root, but a 2nd power does not. So let's raise each term. 8 to the 2nd power is 8 squared is 64. X cubed to the 2nd power, power to power we multiply, so we are using the power of a power property. Actually, it's a product, so power of a product property is what we're using now. Okay. And let's see, 3 times 2 is 6, so that would be x to the 6th. And then y to the 6th raised to the 2nd power, 6 times 2 is 12, so that would be y to the 12th. Okay? All right, so now we need to see, are there any perfect cubes in that radical? And there are. 64 is a perfect cube because 64 is the same as 4 times 4 times 4. So we got 3 4s. X to the 6th is a perfect cube because 6 is divisible by 3. And y to the 12th is a perfect cube because 12 is divisible by 3. Okay, so the cubed root of 4 times 4 times 4 means a 4 gets to come out, because we have a group of 3s, 3 4s. X to the cubed root of x to the 6, 6 divided by 3 is 2, so we'll have an x squared. Y to the 12th cubed root, let's see, 12 divided by 3 is 4, so we'll have a y to the 4th. So 1 over 4x squared y to the 4th is the answer. Sorry, I keep knocking it. All right, letter B. 3 square root of 2 raised to the 5th power. Oh, first of all, I forgot. We need to state what powers we used. We used the negative power property. And we use the power of a product property. Had to finish that answer. All right, so next one, we have 3 square root of 2 raised to the 5th power. So that means that everything in there, that product, has to get that power. So we're using power of a product property again, okay, over 3 square root of 2 raised to the 3rd power. So we're also using power of a product property there as well. Okay, so let's raise 3 to the 5th power. Actually, before I do that, let me rewrite this because I marked all over it. I want to show you an easier way. The numerator and the denominator, if I ignored these exponents, they'd be exactly the same. So that's kind of like saying, what if I had an x to the 5th over an x to the 3rd? Well, then I can cancel out the 3 x's with 3 of them from the top, so it leaves me with an x squared. It's the same concept here. 3 squared root of 2 to the 5th over 3 squared root of 2 to the 3rd. Well, I can cancel out these 3 square root of 2's with 3 of them up here. 5 minus 3 is 2. So then I would just have 3 square root of 2 squared. And now I have to distribute, but it's a much smaller number, so this is a way simpler way. 3 to the 2nd power, 3 times 3 is 9. And anytime you square a square root, the number inside gets to come out, so that 2 gets to come out and has to multiply with the 9. 9 times 2 is 18. Okay, so we were using power of product property because we used that here. That's where we actually used it. And then we also divided. That's how we canceled that 3 squared root of 2 to the 3rd out. We used the power of a quotient property. So we used power of a product property and power of quotient property. Okay. When you write a radical expression using fractional exponents, you can use property of exponents to simplify it. So same things go with fractional exponents. Okay. So we're going to simplify each expression by rewriting it using fractional exponents and using exponent properties. State which exponent property or properties you used. So let's go ahead and take a look at the math tip over on the left, just to remind you how to deal with fractions and radicals, how to switch them back and forth. So if we have a to the m over n power, remember the denominator of that power is the index, so that's the nth root of a to the numerator, so a to the m power. Okay, so let's rewrite this using a fractional exponent. So because of the 3, this is a cubed root. So it's a cubed root of 64x to the 9th. Since all of that is under the cube root, all of that has to be in parentheses, and it's to the 1/3 power because we were taking a cubed root. If it were a square root, it would be to the 1/2 power. If it were a 4th root, it would be to the 1/4 power. No, Ray. She keeps scratching to come inside. All right, so let's go ahead and distribute the power of 1/3. Well, what is that going to look like, Ms. Garcia? It looks like this. 64 to the 1/3 power times x to the 9/3 power. 9 over 1 times 1 over 3 is 9 over 3. Okay, well, let's keep going. 64 to the 1/3 power is the same as saying, let me write it underneath, the cubed root of 64. 64, remember, is 4 times 4 times 4. So since I have a group of 3 4s, a 4 gets to come out. So the cubed root of 64 is a 4, or 64 to the 1/3 is a 4. And 9 over 3 is a 3, so this is an x to the 3rd. So 4x to the 3rd. Okay, so when you see a fractional exponent, you need to be able to think between a radical versus a fraction and how to convert it back and forth. Okay, next one. Cubed root of x times cubed root of x squared. So for this one, oh, what property did we use here? We used power of a product. And yep, that was the only property we used. Power of a product property. All right, for this one, let's see. What I would do is I would just multiply them out, inside numbers with inside numbers, and we get the cubed root of x times x squared is x to the 3rd. And the cubed root of x to the 3rd is, well, that's a perfect cube. So an x gets to come out. Okay. I wouldn't convert that to fractional exponents, so that's why I didn't do that with fractions. It's way easier to do it this way. Okay. So just because we can do something a certain way doesn't mean that that's always the best way to do things. Okay, it's just showing that they mean the same thing. Okay, so that's what gets confusing about these problems, is because there's so many different approaches that all get you to the correct answer. Students get confused because they think that there should only be one right way, but there isn't just one right way. There are multiple ways that will get you to the correct answer. All right, so we're on the last page, page 37, and this is where your homework is going to be. So your homework, your assignment for 3.2 this is page 37, and you are going to be doing numbers 4 through 16. Okay? So make sure you show all your work and upload pictures that are upright facing this way. Please don't submit pictures that are sideways. You know what helps? Don't hold your phone sideways, and it won't do that. Unless you have the lock feature on your phone, then you can take it sideways and it'll still keep it vertical. All right? So anyways, have a great day. I'll see you next time.